Superluminal speeds, or traveling faster than the speed of light, is ruled out by Einstein's theory of special relativity. However, there is still a way by which we can actually travel faster than the speed of light, since we haven't mentioned the medium with reference to which we are talking about. Because as we know that as light moves from one medium to another medium of a relatively high density, it tends to bend and its speed slows down. And we can also calculate the speed of light in that medium by using the above formula. So if you take a charged particle and if you accelerate it in a particular medium faster than the phase velocity of light in that medium, then that accelerating particle will let off an electromagnetic radiation known as Cherenkov radiation. Pavel Cherenkov was the Soviet physicist who first experimentally discovered Cherenkov radiation, for which he got the 1958 Nobel Prize in Physics. He had also done his doctorate thesis in radioluminescence of uranium salt solution excited by high energy gamma radiations. So, when he experimented with these radioactive salt solutions, he found out that these salt solutions were producing a type of electromagnetic radiations. He also found out that this electromagnetic radiation, which was being produced by the salt solution, was not because of a fluorescent phenomena. The radioactive salt was not producing light because of some electron excitation or forbidden state transition, but instead it was producing the electromagnetic glow on its own. In fact, Marie Curie herself encountered this phenomena of Cherenkov radiation when she was looking at a sample of radium salt solution. However, she did not try to investigate as to why it was happening. In order to understand Cherenkov radiation, let's imagine that there is a charged particle moving in a dielectric medium like water at a particular velocity. As the particle moves, it polarizes and depolarizes the medium, due to which it produces a spherical wavefront of electromagnetic radiation. For a stationary particle, this is the type of spherical wavefronts of photons being produced. But as the particle moves, here is an animation showing its different wavefronts being produced at different locations. Now let us imagine a particle in its trajectory with 6 different locations. At each different location, the particle produces a spherical wavefront of photons which are represented by these 6 wavefronts. And as you can see that the particle trajectory lags behind the spherical wavefront. This is because the particle is traveling slower than the speed of light, hence there is no constructive interference between these wavefronts. However, when the particle is traveling faster than the speed of light, then the wavefronts lag behind the particle trajectory, due to which there is a constructive interference between these wavefronts, producing electromagnetic radiations. And this electromagnetic radiation is Cherenkov radiation itself. It is a type of electromagnetic radiation being produced due to the constructive interference of spherical wavefronts produced by particles traveling faster than the speed of light in a particular dielectric medium. Here is another animation showing these constructive interference, due to which a net conical wavefront of light is produced, which produces light in a conical manner. Here are 6 different locations of particle trajectory which succeeds the wavefront, which causes the constructive interference between these wavefronts of photons, thus producing light or Cherenkov radiation. Now, the constructive interference of these light waves happen because the crest and the troughs of these light waves are in phase with each other, which produces a net electromagnetic radiation. Now, we can also use some basic mathematical trigonometry to calculate the emission angle of the Cherenkov light using the function of the cosine theta. Cherenkov radiation is also used to detect particles such as neutrinos. In Japan, there is a $600 million neutrino observatory which can detect neutrinos using water. It contains 260,000 tons of water just to detect neutrinos being produced in the sun due to nuclear fusion reactors. As these neutrinos travel through the water, they produce charged leptons. These charged leptons mainly include electrons and muons, which produce Cherenkov radiation since they are traveling faster than the speed of light in that particular medium. Cherenkov radiation was also used in a historic experiment of particle physics. The video for that experiment I'll be covering up in the future, so stay tuned for the future video. And thanks for watching.